So what I'm going to report on is relatively recent works I've done over the last year, and there is a large part in joint work with Cyprian and Demeter. Some parts are not, so when I don't specify otherwise, it means that it's a joint work. So what is kind of amazing is that originally these decoupling inequalities were really meant to solve problems in harmonic analysis and PDE. And then curiously it turned out that they have also number theoretic implications that are, I would say, to the least rather shocking. And I mean, I was aware of these implications earlier on before these decoupling things were shown. And this, in fact, was one of the reasons I did not really believe in it, because it gave consequences, say, of arithmetical nature, which were kind of too good to, I mean, which were definitely beyond standard methods to prove them, and somehow too good to believe. Also then eventually it turns out that it gives you an approach to bound exponential sums, which has, say, some implications. So you get some modest progress on the Lindelof conjecture using the method initiated by Bombieri and Enrico and Iwaniec, and which is more than, in fact, little progress, because there is one part of this approach where no one has a completely optimal result in some sense. So what I will do in this talk, since I don't have, this is not that much time, I will mainly focus on those aspects of this theory which has direct number theoretic content in some sense, and not go into other applications to PDEs or to complex analysis. So let me start by mentioning you what this inequality really is. I don't know how I can move here, maybe. Yeah, so the simplest statement is that you would take, say, a nice hypersurface in Rn, and let's assume that you have positive definite second fundamental form. We will also need other situations, and then the inequality in some sense has to be reformulated appropriately, and you get another inequality which looks different but morally has the same strength. So say typical examples, you take a sphere, you take a truncated paraboloid, the sphere being particularly interesting when you're talking about eigenfunctions of tori, the truncated paraboloid being of interest, say, when you study the Schrodinger equation. And I will also mention the cone, for instance, which does not fall exactly in this category, and which is going to be, which is in fact, the decoupling there is the first instance in some sense where this problem was brought up, because it's directly related to the wave equation. And as we will see, this cone also will be used, decoupling for the cone will also be play a role later in applications, say, to the zeta function. So what we do is that we take this hypersurface, then we have a small delta, we take a neighborhood of this hypersurface, and then you break it up in the natural rectangular boxes, which are going to be, so what you're going to have here is a delta in one dimension, and then here you have square root of delta, of course, in d minus 1 dimensions. Now, if you have a more general hypersurface, the natural way to introduce these boxes is, of course, going to be by looking at the principal curvatures, and then you define it that way. So there is a notion of Fourier restriction. Well, when you have a function f and take one of these boxes tau, the Fourier restriction of f to tau is just obtained by restricting the Fourier transform to tau and taking the inverse Fourier transform. That's what the notation f sub tau is. And then what the theorem tells you is that there is an estimate of the LP norm by square function, which is obtained by looking at the different Fourier restrictions to these little caps. You have the corresponding square function, and you get this inequality. And what is very important is the endpoint. This inequality holds up to p at most equal to 2d plus 1 over d minus 1. And there is a factor there, so it's not quite an inequality. There is a little loss there, which is delta minus epsilon, which at the endpoint is necessary, as we will see. If you are in the subcritical regime, it's expected that this delta minus epsilon wouldn't be there, but that seems to be an extremely hard problem, would have very surprising, I mean, very, I would say, rather spectacular applications, arithmetical applications, which are really completely beyond any hope. So removing this delta minus epsilon in the subcritical regime is certainly not an easy thing. So let me first illustrate with the most easy example why this 2d plus 1 over d minus 1 is really the best exponent you can expect. So what you do is that you just take the sphere, you take a delta neighborhood, and you take for f so I may have forgotten to say something. So the assumption is that the Fourier transform of f is contained on this delta neighborhood of S. So what we do is that we just take the function f, which is the inverse Fourier transform of a delta neighborhood of S. So what you see then is that the size of f asymptotically is like delta over 1 plus x d minus 1 over 2, which is basically the decay of the d minus 1 over 2 is the decay of the sphere, right, in dimension d. And because we're going to take a p which is like 2d plus 1 over d minus 1, you get that the LP norm of f, so this is integrable. You get an LP norm which is like delta. Now let's see what happens with the other side, with that square function. Well, what you see is that basically the Fourier restriction to tau, this is going to be, this will essentially be the indicator function of the polar, the geometric polar of tau, multiplied with the volume of tau, which is delta d plus 1 over 2. So when you look at the LP norm, you get this factor delta d plus 1 over 2, and then there is the LP norm of this indicator function of tau polar. So remember, tau is square root delta in d minus 1 dimensions, delta in 1 dimension, so the polar is going to be square root 1 over square root delta in d minus 1 dimensions, 1 over delta in 1 dimension. So in other words, what you get there is 1 over delta d plus 1 over 2p when you take the LP norm of that guy. So you get delta d plus 3 over 4, and when you calculate the square function, well, you get exactly delta. Now, why do you have here delta d plus 3 over 4? Because you substitute p to be 2d plus 1 over d minus 1. So this exponent here becomes d minus 1 over 4. So when you look what's going on here, you get indeed delta d plus 3 over 4, and that's exactly what gets you back the delta. And if you would have taken a larger value of p, you wouldn't have gotten it. So that is one example which saturates this inequality, and there are others. Now, arithmetic problems on the cone, for instance, in the theory of exponential sums, plays a role in various issues. For instance, in the work of Iwaniec and Ososhi, where they improve the error term in the lattice point counting. So if you're dealing with the zeta function, average mean square, we'll come to that later, then you don't exactly have a cone, but you have a perturbed cone, which is in fact an algebraic surface. And so somehow decoupling on such surfaces, say cones, perturbed cones, are going to be useful also beyond the traditional applications which were to, say, PDE's wave equation and complex analysis. So another example which is instructive is the donut in R3, where you have principal curvatures which kind of vary from the location you are. And so then you have to define these caps appropriately. So for instance there, the decoupling equality was proven. Then what is going to be absolutely essential later on is lower dimensional hypersurfaces, and in particular curves. So for instance, when we're going to discuss some of the issues about the zeta functions around what they call the first spacing problem, what will play a role there is decoupling for curves. Now, for curves, the whole picture of the decoupling is not really clear yet. And there is a potential chance that the decoupling for curves, that the optimal result, which we believe is the optimal result, well, could be true. And if proven, it would right away give a proof of, say, the Vinogradov mean value theorem in its strongest form without basically using any... what's that? What they call the Vinogradov mean value theorem. I will come back to that later, which would be really an analysis proof. So at least we cannot rule that out yet. For instance, to give you an example, what is solved is by absolutely remarkable work by Woolley, I will come back on in a moment, is the Vinogradov mean value theorem for degree 3, and that involves the 12th moment. So what you get already from this theory is the 10th moment, which is ways beyond what Roy did, say, which was basically, so I'm talking about the case where you have alpha 1 x, alpha 2 x squared, alpha 3 x cubed, and then you want to study the moments of that in alpha. So the optimal Vinogradov mean value involves a moment which is 12. Say from analysis already you get, with this theory you get 10, and there is no reason why maybe, say logically there is, well, in terms of examples, there is no reason why we shouldn't believe in a decoupling inequality which would have the strength to produce Vinogradov's mean value theorem. So we cannot rule that out. And so what I said is that the picture there for curves is not completely clear yet, and there may be other results ahead. Okay, now to come back to what I said in the beginning, what were the original motivations? Well, like I said, they were really related to the cone, and that had to do with smoothing for the wave equation, and also in complex analysis there are some issues about Bergman projections. I will not discuss that because there is less arithmetic in there. On the other hand, then slightly later in the early 90s, I came across that kind of problem in the study of Schrodinger equations on TORI in irrational TORI, which carries an arithmetical component we didn't really know how to deal with in general. And no, sometimes this is really the amazing thing, is that this theory allows you to solve arithmetical problems without doing any arithmetic, which is rather fishy, but somehow that is what it turns out for. Now, a similar example are eigenfunctions bounds on tori. Again, you have to understand things about lattice points on spheres. No access in higher dimension by arithmetical means, and somehow this thing gets you results. Now, what is more recent are the applications to DIOPHANTINE to say integral solutions of systems. This is in the spirit of Vinogradov's inequality and so on, and also applications to exponential sums. So what I will do, like I said, is concentrate more on these arithmetical applications. So let us start by doing a simple, just to show you the strength of this thing right away, by doing a simple application. So we take an S, say smooth with positive curvature, take for S, for instance, the sphere, and then you blow up S with a factor lambda, so you get a sphere of large radius. Then what you can do is, so in the case of a sphere, you would be looking at lattice points on that sphere, and you can start looking at this trigonometric polynomial. You don't have exactly a function, because what you have is discrete points on the sphere, but you can turn that into a function, because what we're going to do is restrict, say, if the parameter there is lambda, we're going to restrict ourselves to an, so we scale it back. Instead of taking the lattice points on lambda s, we are dividing then by lambda, and we're getting points on the unit sphere, and we're going to study that on a ball which is of radius 1 over lambda squared. So of course you can fatten up, I mean this is a standard procedure in harmonic analysis, you can fatten up this point distribution to get a function to which you can apply the decoupling inequality. And so what you have, what you get, and this is in fact the only place where you use something like arithmetic, is that what you're going to get is an LP inequality on a large domain, but because you have a function here which is periodic, eventually everything you get on a large box can be reformulated in terms of behavior on the unit box of size 1, because the thing is periodic. So what you get are bounds on these creatures, LP bounds, which are almost the right bounds. Say if you wouldn't have the lambda to epsilon, it would be the right bound, and for p up to 2d plus 1 over d minus 1. Now, if you think what is known, if you take d equals 3, then what you get there is exponent 4. Now, presently, the best you can prove about, say, eigenfunctions on tori, I will come back to that in a moment, in 3D, is that same inequality. And that proof would require a little bit of arithmetic. I mean, you use some divisor function at estimate at some point, and comes with a lambda to the epsilon. Now, starting from, well, in dimension 4, the correct exponent. So, in fact, the truth is that in dimension 3, for lattice points on the, well, I mean, for the eigenfunctions of T3, what is expected is that you have, in fact, an LP control not only up to 4, but up to 6, 6 not included, which is not proven. In dimension 4, the exponent would become 4 up to 4. What that formula is going to give you there is 10 over 3. And then starting from dimension 5, you have no L4 inequalities anymore. So what this thing is going to give you is a non-trivial bound on LP moments, which is almost the right behavior with the L2 norm, without having the estimate in L4. So for those who know a little bit of analysis, you should realize that it's very, very difficult to get estimates in LP on deterministic polynomials when you cannot derive it, say, from interpolation between even values of P, where you can complete it, where you can really compute it algebraically. So here you get almost correct inequalities, which you do not get by interpolation between even values of P. There are not many instances where you can prove that kind of thing. So if you had a systematic theory to prove that kind of inequalities, then many problems would be solved. But in any case, this is one of the instances where you get that kind of thing. Also note that when you let D being large, what you will get are explicit, say, Hilbertian subspaces of the space L1n. Say this is of some interest in computer science, which would be of dimension n1 minus epsilon with a distortion which is, say, n to the epsilon. And say constructing such subspaces for a long time was an open problem. Eventually it was solved by Rasborov. And that gives you right away such examples. Now, of course, like I said, as a corollary, you find estimates on the eigenfunctions of the d-dimensional torus, which are almost satisfactory. If you could remove the e to the epsilon, it would even be better, but we don't know how to remove the e to the epsilon, because there is this lambda to the delta minus epsilon sitting there as a factor. And you get them controlled up to p at most equal to 2d plus 1 over d minus 1. Just to put that quickly in perspective, this is an estimate, a result of Hermander initially, and then was later developed in full generality by Sock. So what is a situation if you have a manifold, d-dimensional manifold, and you're looking compact smooth manifold, you're looking at eigenfunctions of that? Well, what happens is that you will get a bound of LP norms by L2 norms. And they will carry a factor, which is lambda at some power, and this power depends on P. So, for instance, when P is infinity, you're going to have e at the power d minus 1 over 4, which is saturated for the sphere. And there is, what you should remember from that is that there is an interpolation going on there, but this interpolation between 2 and infinity, it's not a straight interpolation because there's a breaking point. This breaking point is 2d plus 1 over d minus 1. So there is interpolation between 2 and 2d plus 1 over d minus 1, and then 2d plus 1 over d minus 1 and infinity. And that is, and these estimates are optimal and they are saturated for the sphere. On the other hand, if you're looking at TORI, there's another phenomenon going on there, and the breaking point is different. The breaking point is 2d over d minus 2, where you interpolate between 2 and 2d over d minus 2, and then 2d over d minus 2 infinity. Amazingly, in the hyperbolic, at least in the arithmetic hyperbolic case, people believe that there is a similar phenomenon going on for some mysterious reason nobody really understands. But in any case, say, for instance, for hyperbolic surfaces, for instance, similarly to the torus, what one expects is that you would have, correct me if I'm not saying something which is wrong, is that you would have a control of all the finite moments. Okay. Now, it would be very interesting, this is something which is maybe worth to explore, is that whether this decoupling technique in harmonic analysis may have some applications also to treat, at least in certain special cases, get some new information on the eigenfunctions of hyperbolic manifolds and perhaps getting new results there. This is something which is certainly not obvious, but it's not completely ruled out, since there is some kind of at least numerical analogy between these two things. So what is done towards this result? So what I said before is somehow contributing to that, except that I can't take the P all the way to 2d over d minus 2 and stack basically at 2d plus 1 over d minus 1. And most importantly, there is a small factor there, which would be very nice to remove. That's basically what is the problem, is to have a uniform LP bound for eigenfunctions of the Tori, say, beyond dimension 2. So for dimension 2, you have this old estimate of Cook and Zygmunt, which gets you control of the L4 now. Basically, that is it. If you want any other uniform control in any dimension, for P greater than 2, nothing is known. Now, what happens on the other side? So in terms of the supercritical regime, you can prove this estimate provided P is larger than 2D minus 1 or D minus 3, which is a bit larger than the exponent which is here, by combining the first result with some things which were done earlier, which is basically an inequality of that type, a distribution inequality, which is obtained by completely different methods, which is basically obtained. I actually forgot to say something here. This is for D at least equal to 4, right? Because then you can use other techniques. You can use Hardy-Littlewood, Klosterman, circle method type techniques to get, I mean, you should see the distribution as a mountain, right? So basically you have to understand what happens near the top. So this is what happens near the top. That uses more the analytical Hardy-Littlewood, Klosterman, circle method type technique. Then you have to see what happens below, and what happens below isn't captured by that thing. So in any case, this is the best one knows presently about distributions of TORI eigenfunctions, and I doubt it will be improved that quickly. Anyway, feel free to try. So now, the other thing, Schrodinger equations. Well, basically, if you study nonlinear Schrodinger equations, the first thing you have to start understanding is linear Schrodinger equations. Now, what governs the behavior of the linear Schrodinger equation is what they call Strichartz inequalities. These Strichartz inequalities are very well understood on RD. They were much less, they are much less understood when you deal with Schrodinger on a manifold, and in particular on tori. So in the case of a torus or an irrational torus, the solution to the linear Schrodinger equation can be written explicitly as an exponential sum. So you realize, you see right away the x and the t frequencies, so that when you take a Laplacian in x automatically, you're going to have a xi square, which is going to get you the I dt derivative. So you see that this is indeed the solution to the linear Schrodinger equation. So one has to understand the mapping properties of this thing. So, and say more generally, when you take irrational tori, then you have to replace xi squared by a quadratic form xi. So what is really the situation in the periodic case? Well, let's start with dimension d equals 1. So the critical exponent there is 6, and you can prove an inequality just by simple arithmetics, which tells you that the L6 norm is going to be controlled by the L2 norm up to a small divergency factor when you go in the high modes, in the high frequencies. Which is, well, then you can ask, fine, can you put me a constant here? And the answer is no, because it's easy to see that if you take all the coefficients the same, 1 over square root of r, in fact, this L6 norm is not bounded, but is going to behave like log r to the power 1 over 6. So maybe r to the epsilon can be improved to a logarithmic factor, which is not known, but in any case, you cannot put a constant. Note that here, in fact, you are in a situation of decoupling on a curve. So the exponent is 6. And that example shows you, for instance, why you cannot expect to have a constant at the critical exponent, because you have this divergency there. So what this decoupling gives is another way to get that kind of inequality without going into the arithmetics. The same holds for d equals 2, where now the exponent is 4, which is, well, I mean, if you take, so you're talking about Schrodinger in two spatial dimensions and one time dimension. So you have a three-dimensional, you have three variables, and you have a two-dimensional parabola, truncated parabola. And so there the exponent is 4. So again, this proven by basically elementary arithmetics, which can be replaced by this decoupling approach. But what is more interesting is that for d larger, because your exponent goes under 4, the arithmetic doesn't perform anymore. So on the other hand, the results you get from the decoupling, they give you the full picture. And not only that, but even for irrational tori, where even in low dimension you can't do, I mean, you can't start playing Hardy-Littlewood when you have general coefficients there, because some coefficients have that kind of approximation property, some coefficients have other approximation properties. So basically this technique of well, neither an arithmetic technique, of course, or a Hardy-Littlewood type method seems to work well for generally rational tori. Again, the decoupling gives you the full answer. So what you get there, as a result, is the correct Strichartz inequality in the case of tori and irrational tori, which was an issue that was believed to be very hard even for flat tori, exactly because of this reason that we don't know arithmetically how to calculate the p norm when p is not an even integer, right? And the effect of that is that you basically get roughly the same, at least locally, the same local posedness for nonlinear Schrodinger on flat tori as the classical theory for Schrodinger, nonlinear Schrodinger on RD. I mean, this is one consequence of it. I wanted to mention it because definitely there is an arithmetic issue going on. Also, it shows clearly why you have a divergency necessarily at the endpoint. Now, the truth is that this, well, the proof of the result in 2D for curves already have considerable mileage, I will show you. And in fact, this proof could have been found many years ago. I will not get into details, but you use all the ingredients, say, of what you may call classical, say, not classical, but modern harmonic analysis. So there's wave packet decompositions. Then, of course, because you work on different scales, there's parabolic rescaling. Then there is multilinear harmonic analysis. So in 2D, this multilinear harmonic analysis, so you have bilinear square field inequalities. They were already known in the 70s. In higher dimension, they were only developed later by people like Bennett, Carberry, and Tau. This, of course, is a place where it touches upon issues like Stein restriction theorem, Kakeya sets, etc., which are open problems, but they can be solved in some way when you are in a multilinear context because you gain transversality. And so in general dimension, this was done in 06. What I should mention is that now there is a very elegant proof, in fact, by Larry Good, of these things, which basically uses algebraic methods in a purely analytical setting. And so it's reasonably elementary. Now, what is somehow diabolical in this proof is that the whole thing works with a multiscale bootstrap. And, well, you have to see to believe it. But say in 2 dimensions, the reason why it wasn't done earlier is that people just didn't notice that you could do such a bootstrap. And it really comes from trial and error, is that you find recursive inequalities, and eventually, by writing things down on different scales and iterating, you find what you want. So I would say that basically this proof in 2D can be given from scratch in maybe 45 minutes or something like that. And somehow the highlight is this bootstrap. Let's put it like that. Now, what is this transversality? What is this Bennett-Carberry-Tau theorem? It is the following. So this is a quite powerful result. So let's say we have a compact smooth hypersurface. You don't have to assume that you have positive curvature, but what I want to take are these disjoint patches, so that when you take the corresponding, so you have d of them, when you look at the normal vectors and you take the wedge product, it's not degenerate. You have a control of that. So they are in transversal position. Then you take, let's say, measures mu1, mu2, mu_d, which are supported on these patches. And the assumption is that these measures, so they're absolutely continuous with respect to the surface measure, and say they have an L2 density. Now, so that thing is controlled. What it turns out is that you can control, you don't control the LP norm of one measure, but because of the transversality, when you take the geometric average of the Fourier transforms of these measures, of these D measures, then you have a control of the LP norm. And the reason why somehow this works better is that there is a certain transversality there, which allows you to say things which you can't say in general. So if you would look at the full measure mu, and then you put here the LP norm of mu hat, you don't have this inequality. With an L2 norm there, the best you can do is Strichartz. If you want to do beyond, you want to go beyond the Strichartz exponent, so you want to lower P, here you have to put something which is better than L2. Nevertheless, in this transversal situation, in some sense, you have what you may call a multilinear Strichartz inequality, with here still an L2. And then what happens here is that you lower the P all the way to the 2D over D minus 1. If you would write Strichartz equality, it would be 2D plus 1 over D. But you lower it all the way to 2D over D minus 1, which is really the exponent from the Stein restriction conjecture that you will have if you would put here, for instance, instead of an L2 norm, you put an L infinity norm. So this is a rather... But yeah, it just happens to be. It's just, I would have to look at, maybe Gut removed it, it could be. I have to look, actually it's a good point, because there is a sharp version of it. So no, let's be careful. In the subcritical regime, maybe. In the critical regime, you may, I have to be careful. In any case, I'm losing R to the epsilon because of my iteration anyway, so I just wanted to use the first result here. Now, I want to talk in the remainder, I will talk about the arithmetical consequences of that, which in a way, I have to admit for me, were a red flag, because these were statements I didn't know how to even approach by elementary, by say, standard means. So let's look at the Segre surface and integer points on that. So there is a result by Roy. So you can express this, of course, as a mean value, which is basically giving you an n to the, maybe n to the 3 plus epsilon, or basically a little bit off from n to the 3, just by elementary means. And there is a key identity which comes up in any kind of treatment, which allows you, because if I give you these two things, you know the left side. So basically, you know, you have a bound on the number of factors, which is given by divisor function. This is kind of coming up in every proof. Now, what I'm going to do is proving a stronger result, which does not use any divisor functions at all, which is rather strange. So the Segre surface problem has a small history. There's important work by, it's of course very closely related to wiring problem issues, Vaughan and Woolley, who proved that actually there is no divergency there, and in fact the correct main term for the number of solutions, which comes from the degenerate solutions, is 6n cubed. And then there is an error which is of smaller size. And in fact, this is correct, but somehow these upper bounds are matched by the, well, in that case, is by the lower bounds. Yeah. No, but you're absolutely right. The decoupling inequality is a one-sided inequality. It's not an equivalence. That's very important. Thank you. They even went out of their way to specify what is the asymptotic distribution of UN, if you care about that. But let me say, first of all, that this is not the correct inequality. And, well, this inequality is correct. I don't say that. But it is not the correct inequality. A small difference. Because really what one expects is not an exponent 6, but in fact, the right exponent should be the exponent 8. So that is still open. And this is a very nice problem. This is still unsolved. What is known, the best which is known towards the 8th moment is a result which is gotten as a consequence of Woolley's work on the mean, on Vinogrado's mean value theorem, which is completely solved in the cubic case, not yet for higher degrees, and which gives you the right evaluation of that. Why is this the right evaluation? Well, you just check what happens with the diagonal contribution, basically. So the point is that this L6 is not really the right exponent. If you go with an n to the epsilon, it's 8. On the other hand, what the decoupling allows you to prove is something else. Instead of having an equality in the second equation, let's write an inequality with capital N here, which buys you one more variable. So you have, in fact, 7 variables. You have N1, N6, and then an N7, where you would put N1 cube plus N2 cube, etc. It's less than, say, equal to something, let's call it N, where N would be bounded by capital N. Now, when you see what is going on there from the perspective of diagonal contributions, well, what happens is that you have 6 variables, and then, well, you can put the 7 down. I don't have to put the 7 on. So that equation is going to cut you 1, right? So you have n to the 5. And then this equation, normally it would cut you 3, but because you put a capital N there, it only cuts you 2. Remains n to the 3. So the expected evaluation of that would be n to the power 3 plus epsilon. Otherwise, you get an inequality, which is the same, basically, as what Roy proved with n3 plus epsilon, except that now you replace the second equation by an inequality, which is capital N. So, and this, like I just showed you, is best possible. Now, what was for me a red flag at the time is that I have no way to prove this by any other means. And what is also amazing is that in particular, you get a proof of that without using this, which is even, I don't know, at least look to me as rather strange. Rather strange. Yes, and that does not use it. So this is also why, for a while, I was kind of, say, not so, how do you say, not so convinced that what I was doing for decoupling was really correct, because you find these strange consequences. To give you another example, there is an inequality which is in the same spirit, which is a mean value theorem of Robert and Sargos. Their proof uses the Bombieri-Iwaniec method, and this inequality has applications to exponential sums and to Weyls inequality with the His-Brown approach, where you get little improvement to the usual Weyl inequality. So it turns out that also this inequality can be gotten using just decoupling, and in fact in a more general form. Now I have to say, what was reassuring to me is that this summer Woolley discovered another approach to this to these results, using his method, which was really the breakthrough in his progress on the form of Vinogradov mean value, but at least he got it in certain cases. So he got it in the cubic case, which is inequality I mentioned before. Now, let me get back to, well, let me go on with something else, which are the consequences to exponential sums. This is kind of an idiotic thing, because it really looks like the records they measure in Olympic Games. And you know why records get broken? Just because they get better and better measure instruments. So before they were calculating the times up to 1/10 of a second, and became 100 of a second, and so on. So this is more or less what it is about. Now, the only reason why I wanted to say something about that is that, in fact, there are only two important steps in this whole story. The first step is the Hardy-Littlewood step. The second step is this one. I mean, the rest is basically derivative. So it's not very nice, but this is what it is. Why is this an important step? Okay, well, let me take it back. Yeah. Well, we're going to discuss how to remove this sentence, perhaps. Why was this an important step? Because it's the first time that people tried to, rather than say approximating, say general exponential sums by quadratic approximation, this is the first time that one started looking at cubic approximations. So estimating cubic exponential sums is not easy, but the good thing is that somehow with this, so at least in certain cases, the coefficient of the highest degree, which is the cubic degree, is small. And that allows you to do Poisson and find an initial leading term, which is still not easy to handle. But what is happening is that when you have a general exponential sum like that, you don't have one cubic exponential sum, but say if you break it up in pieces where you can do an approximation by a cubic sum, you have a whole family of such pieces. So first step is that you divide the big interval, say go from m/2 to n, in short intervals I, say of size n, on which you can replace your exponential sum by a cubic polynomial. And so you have these particular exponential sums with a small factor mu here, for which you can write basically by Poisson summation a leading term. You may call it it's Poisson summation for perturbed Gauss sums or perturbed quadratic sums, something like that. So then the problem is to deal with an estimate in the mean over this family of exponential sums. So this is now a second story, and so this was the second step. So after Poisson summation, what you're going to have is another beast, which is written here. So this is another sum. It's another exponential sum with a parameter, with now a variable which is h and ranges up to something, say capital H. And there are coefficients here, well, B1, B2, B3, B4. And this B1, B2, B3, B4, of course, they will depend on A1, A2, and mu. And these A1, A2, and mu, they depend they depend on the particular interval I, where you have approximated this exponential sum by your cubic polynomial. So if you have that kind of situation, I mean, the obvious way to handle it is to try a large CIF. I mean, to put it down to earth, you basically try to handle it with a Cauchy-Schwarz or a Hölder technique, where in some way you want to understand the distribution of B1, B2, B3, B4 when you move the interval. This is what is usually called the second spacing problem. And then you want to apply a Hölder inequality to start looking at a moment where B1, B2, B3, B4 are going to be variables which are going to vary in some parallelepiped. So that, at that moment, leads you to a certain mean value problem of the type of Vinogradov mean value theorem, except that here you don't have a polynomial, but you have specific, well, I mean, these powers are quite important. You get h squared, h3 over 2, h a half. So there are two problems there which are quite non-trivial, and well, if you want to convince yourself, you should look at Huxley's book. He wrote the whole book about that, and then there are many papers later on, and this is the kind of thing you look at, but I don't think you want to read. So at least this was my personal experience. So in any case, the first thing, well, one step is to understand the distribution of B1i. This is a sentence you should probably also remove. B1i, B2i, B3i, B4i when you vary the interval. So that is what they call the second spacing problem, which is still not completely solved. Now, once you have it reduced, let's say, once you understand that, you apply a Hölder inequality, automatically you're ending up with a mean value problem, which is what is called the first spacing problem. Why is it called the first spacing? Because when you work out, usually you work with even powers here for some reason. You will see that there's no loss there. Then this evaluation amounts to checking the number of solutions in integers, say, from 1 up to h, of an equation which is going to be an exact linear equation in h, an exact linear, not quadratic equation in h, and then here you're going to have an equation in hi to the power 3 halves, there in hi to the power half, which is not going to be an equality, but is going to carry a corresponding, say it will be in fact, I mean, an inequality of the type, so h1 at the power 3 halves plus h2 at the power 3 halves up to k, minus hk minus 1 3 halves, etc. up to 2k. The size of that thing should be bounded, when you look what it means, should be bounded by 1 over square root of h. So the two last equations are in fact not equalities, but are inequalities. So there's a second paper then, by the same authors, where they deal with this problem, and they prove that, in fact, they are not going, they're taking something which is a little bit simple. They don't deal with this last term. So what they're proving is an 8-moment inequality, which is the correct bound. So the first step is that, in fact, excuse me. Yes, that is very correct. So in any case, what they realized at some point is that you could get this inequality also from a decoupling. In fact, a decoupling for curves. And then you start looking at some more in the literature. Then there is a later inequality which deals with that, say in its full glory, with the 4 variables there, which is not treated. Why do I write up to 6? Because somehow 6 is the right exponent there. We'll come back on that. So what they do is that they get the right bound for akh for k equals 5, which is h at the power 5 plus epsilon, which you get again just by looking at, let's put it like that. You see that this is indeed what is obtained. But you also see that somehow there is some room there, and that in fact, with that kind of inequality, if you want to have a bound, in the sense that it's the diagonal which dominates the picture, then the the real exponent there is k equals 6. So in terms of the first spacing problem, the optimal exponent is k equals 6. So what it turned out is that they can get this optimal exponent there. So in some sense, the first spacing problem is completely solved. And this is what gives you. So in terms of the spacing, the second spacing problem, use the available results, which were developed in a number of papers. You have you have the book, and then you have Huxley-Kolesnik, and then there is Huxley 3, 4, 5, etc. So you get that, and that is not optimal. There are later results. So this improves you 1 decimal on the. Actually, it's on the 3rd place. But don't fool yourself. In exponential sense, people have worked much harder to get much less. I can tell you. To give you an example, so this is not optimal, and you can use, for instance, the results on the second spacing problem developed by Huxley in Huxley 5, for instance. I mean, this is a 40, 50-page long paper, and that would get you a saving on the 5th decimal per unit. So I didn't think this was worth to. Also, to implement these results is not completely trivial. So what is underlying there? It's a decoupling for curves. So like I said, not the whole picture is clear for curves, but these stem results are proven. And so this is one result, which is, in some sense, the bone in the argument to treat that first spacing problem. So what you have is a curve with full torsion. So take the Frenet basis, is non-degenerate. Then what I will consider are disjoint arcs. So it's a multilinear inequality, otherwise it's not true. And in that case, I will need d over 2 disjoint arcs. So it's a multilinear inequality. And at some point, of course, you have to get to a linear inequality. So there is a certain strategy to go from multilinear to linear, which was, in fact, one of the very nice discoveries of Larry Good. And, so we used that in a certain number of places. That this is basically how the multilinear theory of Bennett-Carberry tau can be used to prove really to contribute to the original problems in some sense. But here we'll keep it in the multilinear form. So what is now the decoupling for curves? Well, the same thing. You would take a delta neighborhood of the curve, and then you would start looking at cubes which are of size square root delta. So they are just regular small cylinders. Their thickness is delta. Their length is square root of delta. So then you have take functions which are supported in a delta neighborhood of this curve, and you do Fourier restriction by just breaking it apart, just restricting to these different cubes, and you have the multilinear version of it. So in that case, you have d over 2 big arcs. Each of these arcs is subdivided in these tubes, which are tubes of that form, and then you do Fourier restriction to these different tubes. And then you get a decoupling inequality, which is a multilinear inequality, which is the correct inequality. In case we are dealing with, I have to remember what is d. I believe I work with d equals 4. So we are working here with the 12th moment, which is exactly the moment we need here for k equals 6, right? So, in some sense, this is the key inequality which is used. Amazingly, this inequality is a consequence, again, of the 2-dimensional L6 decoupling inequality. So just to say that in this 2-dimensional L6 decoupling inequality, there's quite a bit of knowledge. So once you have this inequality, then you have to massage this a little bit, work a little bit more, and eventually what you can get out of it is that bound. So, made some progress and then started wondering, well, you look some more in Huxley's book, is there other questions maybe that you can make progress also? So there is some very recent work which is actually joint with Nagel-Watt, who is probably the leading expert in the second, what they call the second spacing problem. Don't underestimate this thing. This is not a trivial matter, this business. So the mean square of the zeta function, what you do is that you take the integral on an interval. You should think it of a small interval 0t, and then you subtract what are supposed to be the leading terms, and you want to bound the error term. So this is an interesting story, because if you do that, of course, your interval is not long enough to apply directly Bombieri-Iwaniec. So what you do is an alternative, is an intermediate step, which is van der Korpel differencing. So instead of having an exponential sum then in one variable, you have an exponential in one summation variable, you have an exponential sum in two variables. So the first spacing problem becomes really an arithmetical problem in two variables, and this turns out to be a problem about, some sense, counting lattice points on, some sense, not on a cone, but on a perturbed cone. So this has an interesting story, because the first time where this kind of questions with cone appeared is in the work of Iwaniec and Mososhi on the lattice point problem, which came after the Bombieri-Iwaniec, if I'm correct, where the first spacing problem is a very nice arithmetical problem about solutions or which involves really points on cones. So then, well, this had a clean answer and was the best possible, basically the best possible result. Then what people tried was to deal with this perturbed cone by looking at it as a perturbation of the cone and trying to get around the problem of the perturbation. And this, well, I mean, this gives you something, but it never really gave you the same, a result of the same strength as what you got from having a clean cone. Eventually, the problem got solved by what? In paper which appeared in 010, where he got essentially the same exponent as what you will get in the case of a clean cone. So you have to, he's basically using the special structure of this perturbed cone in some nice way to recover the results for the cone. So in some sense, although say whatever better we're getting is not very spectacular, it's, well, almost again, well, I mean, it's on the fourth decimal, some cases near the third decimal. So what turns out is that this perturbation of the cone is not only a nuisance, it's not really a nuisance, and that eventually can be solved, it's a help. Because the perturbation of the cone, remember when I spoke about principal curvatures, now make sure that one principal curvature is not exactly 0 anymore. So basically you get a better decoupling inequality than for the cone, which is useful. So what is really the role of this decoupling? It's very simple. Before you really dig, like what happened in the case of the cone, for instance, in pure arithmetical problems, and then you do it any way you can, using divisor functions, etc., there is a preliminary reduction of the problem where you reduce these arithmetical problems to smaller regions. And that comes from the decoupling. And then basically this arithmetic is restricted to smaller regions, which gives you a chance to get more accurate things. So the bottom line is that we could improve in a not so spectacular way, but like I said, people have worked more to get less, the case of the error term in the mean square. And in fact, we also get a bound for if you don't, I mean, remove this junk, you just look at it like that, and then you want to have a bound, say, on the short interval. How well can you bound the square of the zeta function, say, average L2 norm, on an interval of size u? Well, of course, the longer the u is, the better, right? So you want to get u as small as possible. So what we can basically do is getting intervals which are, say, t at some 3, 1, 4, 0. So when you compare with what was gotten here, it's almost again on the the second, on the third decimal. And well, in this kind of problem, they call it exponential sums with a parameter. Essentially, the issues about the second spacing problem are very much the same as in the one parameter family. What is changing is the first spacing problem. So as far as the second spacing problem is concerned, what we used are old estimates which were developed by Huxley and Watt, and they are not the best possible. Essentially, another reason why I mentioned to you this idiotic table here is that in some sense there is a limit with what one gets with this method, and basically this limit would be 0.15. So if somehow it would turn out that you could solve the second spacing problem completely, you would get the right result, but somehow this seems to be difficult. I think I will stop here. I'm just in time. So I'm open to any questions.